So here's something worth thinking about as you settle in tonight. Right now, probably within arm's reach of wherever you're lying, there's a device. Your phone, your tablet, maybe a laptop on the nightstand. And inside that device, something truly wild is happening. Billions of tiny switches are flipping on and off, millions of times every second. Not mechanical switches, not anything you could see with your eyes or hear or feel. Electrical switches, microscopic, etched into a sliver of silicon no bigger than your thumbnail. And each one of those switches is doing something absurdly simple. It's either on or it's off. That's it. That's all it can do. And yet, somehow, billions of those trivial on or off decisions, happening unimaginably fast, are enough to produce everything your computer does. Every photo, every video, every word on every screen, every calculation, every song, every map, every message you've ever sent. All of it comes down to tiny switches saying yes or no, 1 billion times a second. And if that sounds like it shouldn't work, if it sounds like there's no way something that simple could give you the entire digital world, then you're feeling exactly the right thing. Because the story of how we got from the idea of a switch to the device in your pocket is one of the most extraordinary stories in human history. It involves war and mathematics, and failure and obsession. It involves a shy English genius who probably saved millions of lives and was then destroyed by his own government. It involves physicists who stumbled onto a discovery in a cramped New Jersey lab that would reshape civilization. It involves a quiet revolution in logic that happened in the 1800s, decades before anyone had electricity in their homes, carried out by a self-taught English mathematician who believed he had found the laws of thought itself. And that's what we're going to walk through tonight, how computers actually work. Not in the hand-wavy, metaphorical sense, but really, what's happening in there? How does a machine made of sand and metal and electricity manage to do math, store memories, run programs, display images, connect you to someone on the other side of the planet? We're going to start from the very beginning, go slow, and build it up piece by piece. No rush at all. If you drift off somewhere in the middle, that's completely fine. This stuff will still be here. And honestly, there's something kind of perfect about falling asleep to the story of how machines learn to think, while the thinking machine next to your bed keeps quietly doing its thing, switch after switch after switch, all through the night. Let's start where all of it starts, which is counting, because that's really what a computer is. At bottom, it's a counting machine, an absurdly fast, absurdly versatile counting machine, but a counting machine all the same. And humans have been building counting machines for a very, very long time. Go back about 5,000 years to ancient Mesopotamia, the land between the Tigris and Euphrates rivers in what's now Iraq. The Sumerians are running one of the first complex civilizations on Earth. They've got cities, agriculture, trade networks, taxes. And taxes mean you need to keep track of things. How many bushels of grain came in this season? How many sheep are in the flock? How much you owe the temple? So they developed some of the earliest known counting tools, clay tokens, small-shaped objects that represented specific quantities of specific goods, a cone for a small measure of grain, a sphere for a larger one. You could put them in a clay envelope, seal it, and you had a record. It was physical counting, tangible. You could hold the math in your hand, and then, somewhere around 2500 BCE, give or take a few centuries, something interesting shows up in the archaeological record, the abacus, or at least early versions of it. Counting boards with grooves or lines, where you'd slide stones or beads to represent numbers. The word calculus actually comes from the Latin word for pebble, because that's what the Romans used on their counting boards, little pebbles. And the beautiful thing about an abacus is that it's not just storing numbers, it's computing with them. A skilled abacus operator can add, subtract, multiply, and divide just by sliding beads along rods. There are competitive abacus users in Japan and China, even today, who can outrace people using electronic calculators for certain types of problems. The tool is thousands of years old, and it still works. But here's what matters about the abacus for our story. It introduces a principle that turns out to be absolutely fundamental to how computers work: positional notation. On an abacus, the same bead means different things depending on which row it's on. A bead on the ones row represents 1. The same bead on the tens row represents 10. On the hundreds row, 100. The bead itself is identical. Its meaning depends entirely on its position. That's the same principle behind our number system. The digit 3 means 3, or 30, or 300, depending on where it sits. And it's the same principle behind binary, the number system that every computer on Earth runs on. But we'll get to that in a while. For thousands of years, the abacus was essentially the state-of-the-art in computing technology. Variations of it spread across the ancient world: Mesopotamia, China, Rome, medieval Europe. It was fast, reliable, and portable. But it had a limitation. It required a human operator. The person did the thinking. They decided which operation to perform, in what order, what to do with the result. The abacus was a tool, like a hammer, powerful, but inert. It didn't do anything on its own. The first real attempt to build a machine that could do arithmetic by itself, that could turn a crank and get an answer without a human doing the mental work, didn't come until the 17th century, and it came from, of all people, a teenager. Blaise Pascal was born in 1623 in Clermont-Ferrand, France. His father, Etienne, was a tax commissioner and a talented mathematician in his own right. Young Blaise was a prodigy. Genuinely, not in the inflated way we sometimes use that word. By the age of 12, he'd supposedly worked out many of the propositions in Euclid's geometry on his own, without being taught. By 16, he wrote a significant paper on conic sections that impressed some of the leading mathematicians in Paris. And at 19, he did something that nobody had ever done before. He built a working mechanical calculator. The story goes that Pascal built it to help his father, who had been appointed tax commissioner for the region of Rouen in Normandy. Etienne's job involved enormous amounts of tedious arithmetic, adding up long columns of figures, converting between different units of French currency, which at the time involved a maddening system based on subdivisions of 12 and 20, not the clean decimal system we use now. Young Blaise watched his father grinding through these calculations night after night and thought, there has to be a better way. What he built, starting around 1642 and refining over several years, was a device called the Pascaline. It was a brass box, about the size of a shoebox, with a row of numbered wheels on top. Each wheel had the digits 0 through 9 around its edge. To add a number, you'd use a stylus to turn the appropriate wheel. The clever bit was the carry mechanism. When a wheel turned past 9, it would engage a small tooth that would advance the next wheel by 1, automatically carrying the 1, the same way you do on paper when a column adds up to more than 9. Turn the 1's wheel past 9, and the 10's wheel clicks forward by 1. Turn the 10's wheel past 9, and the 100's wheel advances. Automatic, mechanical carrying. Think about what that means. For the first time in history, a machine was doing part of the intellectual labor of arithmetic. Not all of it. You still had to input the numbers and read the output, but the actual grunt work of addition and carrying was being done by gears and springs, not by a human brain. It was slow and expensive to build. Pascal made about 50 of them over a decade. each one handcrafted, and they were finicky. The manufacturing tolerances of 17th-century French craftsmanship weren't always up to the precision the mechanism demanded. Most of them didn't sell well. But the principle was proven. Arithmetic could be mechanized. And about 30 years later, another mathematician took the idea further. Gottfried Wilhelm Leibniz. And if that name rings a bell, it's probably because he independently invented calculus at around the same time as Isaac Newton, leading to one of the most bitter intellectual feuds in the history of science. Leibniz was a polymath in the truest sense: philosopher, mathematician, diplomat, historian, engineer. He was working at multiple courts across Germany, advising royals, trying to unify the churches, writing thousands of letters. And in 1694, he built a calculating machine called the stepped reckoner that could do something Pascal's couldn't. It could multiply and divide, not just add and subtract. Leibniz's machine used a special gear he invented called the Leibniz wheel, or stepped drum, a cylinder with teeth of varying lengths around its surface. By sliding the drum to different positions, you could set different digits, and the rotation of the drum would perform multiplication through repeated addition. It was ingenious, and the stepped drum mechanism would show up in calculating machines for the next 300 years. But here's the thing about Leibniz that's even more important for our story than his calculating machine. In 1679, Leibniz wrote a paper, never published during his lifetime, in which he described the binary number system, zeros and ones. He showed that any number could be represented using only 2 digits, and that arithmetic could be performed in binary just as easily as in decimal. He even drew up tables of binary addition and multiplication. Now, Leibniz was partly motivated by philosophical and theological ideas. He saw a metaphor in binary, with 1 representing God and 0 representing the void, creation from nothing. But the mathematical insight was real, and it was profound. Any quantity, any number, no matter how large or complex, can be built from nothing but zeros and ones. Leibniz couldn't have known it, but that insight would become the foundation of the entire digital age. Every computer ever built runs on binary. Every piece of data in the digital world, every photo, every song, every email, every line of code, is ultimately stored as a sequence of zeros and ones. And the reason isn't mystical or arbitrary. It's practical, because the simplest possible switch has 2 states, on and off. And if you use on to represent 1 and off to represent 0, then any switch can store a binary digit. Any collection of switches can store a binary number. And if you can figure out how to combine switches in clever ways, you can do binary arithmetic. And if you can do binary arithmetic, you can compute anything. But in Leibniz's time, nobody had switches like that. Nobody had electricity. The binary insight sat there, beautiful and useless, for about 250 years. Meanwhile, the quest for better calculating machines kept churning forward, 1 gear and 1 crank at a time. Dozens of inventors across Europe built variations on Pascal's and Leibniz's designs. The arithmometer, built by Thomas de Colmar in the 1820s, became the first mass-produced calculator and stayed in production for nearly a century. Mechanical calculation was becoming routine, a standard tool of business and science. But all of these machines could only do what you told them to do in the moment. They couldn't follow a sequence of instructions. They couldn't make decisions. They couldn't take the result of one calculation and feed it into the next automatically. They were calculators, not computers. And the difference between a calculator and a computer turns out to be enormous. It's the difference between a tool and a mind. A calculator does what you ask. A computer does what you program. And the first person to clearly envision a machine that could be programmed, a true general-purpose computer, was an obsessive, irascible English mathematician who spent decades and a fortune trying to build something the technology of his era simply couldn't deliver. His name was Charles Babbage, and his story is both one of the most inspiring and most frustrating in the history of technology. Babbage was born in London in 1791, the son of a wealthy banker. He was sickly as a child, which meant he spent a lot of time at home reading, and he became fascinated with mathematics early. By the time he arrived at Cambridge, he found that he already knew more mathematics than most of his professors, partly because English mathematics at the time was strangely behind the continent. The English were still loyal to Newton's notation for calculus, while the French and Germans had adopted the superior notation of Leibniz, and the English mathematical curriculum was suffering for it. Babbage, along with his friends John Herschel and George Peacock, formed a society to modernize English mathematics, which they half-jokingly called the Analytical Society, dedicated to promoting what they called the principles of pure deism, meaning Leibniz's D notation, against the dot age of the university, a pun on Newton's dot notation and the ossified old guard clinging to it. After Cambridge, Babbage became obsessed with a very specific problem: errors in mathematical tables. This might sound mundane, but in the early 19th century, printed mathematical tables were absolutely critical infrastructure. Navigation, astronomy, engineering, finance, insurance, all of them depended on tables of logarithms, trigonometric functions, interest calculations, and other pre-computed values. And those tables were full of errors. They were computed by hand, by rooms full of human calculators. People whose job was literally called computer, by the way, because that's what the word originally meant, a person who computes, and then typeset by hand and printed. Every step introduced the possibility of mistakes, and mistakes in a navigation table could send a ship onto rocks. Babbage's idea was to eliminate the human error by building a machine that could both calculate the values and print the results directly, cutting out every fallible step. His first design, which he called the difference engine, used a mathematical technique called the method of finite differences to compute polynomial functions through repeated addition. The method is clever. It lets you evaluate complex functions without ever multiplying or dividing, using only addition, which is mechanically much simpler. Babbage demonstrated a small working model to great acclaim. The British government gave him a substantial grant, £17,000 over the years, which was an enormous sum, enough to build 2 warships, to construct a full-scale version. And then things went sideways. Babbage was a perfectionist, endlessly redesigning components before they were finished. He fought with his chief engineer, Joseph Clement, over costs and ownership of the specialized tooling. The project dragged on for over a decade, consuming vast amounts of money, and was never completed. The government eventually cut off funding in 1842, and the partially built difference engine sat in Babbage's workshop like an expensive monument to ambition outrunning technology. But here's the thing: the difference engine, as impressive as it was, is not really what matters about Babbage. What matters is what he designed next, while the difference engine was still stalled. Starting in the mid-1830s, Babbage conceived of something far more ambitious, a machine he called the analytical engine. And this is where the story gets genuinely breathtaking, because the analytical engine was, in every meaningful sense, the design for a general-purpose programmable computer, more than 100 years before the first electronic computers were built. Think about what it had. It had a mill, a processing unit that could perform addition, subtraction, multiplication, and division. It had a store, a memory, that could hold 1,000 numbers of up to 50 digits each. It could take instructions from punched cards. an idea Babbage borrowed from the Jacquard loom, a French weaving machine that used cards with holes punched in them to control the pattern of the weave. Different cards, different pattern. Different cards in the analytical engine, different computation. It could branch, meaning it could examine an intermediate result and decide which instruction to execute next, based on whether a condition was met. It could loop, repeating a set of instructions as many times as needed. It could even print its own results. This is a computer. Input, processing, memory, conditional branching, output. Babbage designed all of it, in incredible mechanical detail, thousands of pages of plans, tens of thousands of individual components, all specified down to individual gear teeth. He never built it, of course. The engineering challenges were immense. The funding wasn't there, and Babbage was difficult to work with, burning through collaborators and alienating supporters. He died in 1871 with the analytical engine unbuilt, but the design was sound. Modern engineers at the Science Museum in London have built portions of Babbage's difference engine from his original plans, and they work exactly as specified. The analytical engine, if it had been built, almost certainly would have worked too. And here's a detail that should give you chills. In the 1990s, when researchers carefully studied Babbage's designs, they realized that the analytical engine was Turing complete. It could, in principle, compute anything that any modern computer can compute. Babbage designed a universal computer in the 1830s. He just couldn't build it with brass gears. And this brings us to the person who saw most clearly what Babbage's machine meant. A person who, in some ways, understood the implications of programmable computing better than Babbage himself. Ada Lovelace, born Augusta Ada Byron in 1815, the only legitimate child of the poet Lord Byron. Ada never knew her father. Byron separated from her mother just weeks after Ada's birth, left England, and died in Greece when Ada was 8. Her mother, determined to steer Ada away from what she saw as Byron's dangerous poetic temperament, had her tutored intensively in mathematics and science. And Ada took to it brilliantly. She met Babbage at a party in London in 1833, when she was just 17. She was fascinated by his difference engine, and over the following years, she became one of the very few people who truly understood what the analytical engine was and what it could do. In 1843, she published a lengthy set of notes on the engine, technically an annotated translation of an article by the Italian military engineer Luigi Menabrea, and those notes are extraordinary. They contain what is widely recognized as the first computer program ever written, a detailed algorithm for the analytical engine to compute Bernoulli numbers, complete with what we'd now call a flowchart showing the sequence of operations. But more important than the specific program was Ada's vision. She grasped that the analytical engine wasn't just a number cruncher, because it operated on symbols, and symbols could represent anything, not just quantities, but notes of music, letters of the alphabet, logical propositions. She wrote that the engine could compose music, produce graphics, and be used for scientific purposes beyond pure calculation. She saw, in 1843, that a general-purpose computing machine could manipulate any kind of information that could be represented symbolically. That's an insight that wouldn't be fully appreciated for another century. She also drew a careful line. The engine, she wrote, has no pretensions to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any truths. It's a tool, not a mind. That distinction. Can a machine only follow instructions, or can it genuinely think, would become one of the central questions of the 20th century, and we'll come back to it. So by the middle of the 1800s, the conceptual foundation is all there. You have mechanical calculation, proven by Pascal and Leibniz and dozens of others. You have the binary number system, described by Leibniz. You have the design for a general-purpose programmable computer, worked out in astonishing detail by Babbage. And you have Ada Lovelace's insight that such a machine could manipulate any kind of symbolic information. All the ideas are in place. What's missing is the technology to make it practical, because gears and cogs and brass springs are too slow, too big, too expensive, and too unreliable for real computation at scale. But there's one more piece of the conceptual puzzle that needs to fall into place before we can get to actual computers. One more idea that seems, at first glance, to have nothing to do with machinery at all. It has to do with logic, with the rules of reasoning. And the person who contributed it was a largely self-taught English mathematician who grew up in poverty, never attended a top university, and believed he had uncovered nothing less than the mathematical laws of the human mind. George Boole was born in 1815 in Lincoln, England, the same year as Ada Lovelace, as it happens, though their paths never crossed. His father was a cobbler who loved science and mathematics but lacked the means to give his children a privileged education. George was mostly self-taught, learning Latin, Greek, French, German, and Italian on his own, and diving deep into mathematics through books he found in local libraries. By his mid-20s, he was publishing original mathematical papers, and by 30, despite having no university degree, he was appointed professor of mathematics at Queen's College in Cork, Ireland, largely on the strength of his published work. In 1854, Boole published a book with one of the most ambitious titles in the history of mathematics, An Investigation of the Laws of Thought, on which are founded the mathematical theories of logic and probabilities. And what Boole did in that book was revolutionary, even though almost nobody realized it at the time. He showed that the rules of logic, the rules by which we reason about true and false statements, could be expressed as a form of algebra. You could write logical propositions as equations. You could manipulate them using mathematical operations. And the whole system only needed two values, true and false, which Boole represented as 1 and 0. Here's what that looks like. Take the logical operation AND. It is raining and it is Tuesday. That combined statement is only true if both parts are true. If it's raining but it's Wednesday, the whole thing is false. Boole represented this as multiplication. 1 times 1 equals 1. True and true equals true. 1 times 0 equals 0. True and false equals false. 0 times 0 equals 0. False and false equals false. The multiplication table for AND is just ordinary multiplication, restricted to zeros and ones. Now take OR. It is raining or it is Tuesday. That's true if either part is true, or both. Boole had a way of expressing this too. And not, the logical negation, is just flipping. Not true is false. Not false is true. Not 1 is 0. Not 0 is 1. With just these three operations, and, or, and not, you can express any logical statement, any chain of reasoning, any rule of deduction. Boole had reduced the entire structure of formal logic to arithmetic with zeros and ones. He had turned thinking, or at least formal reasoning, into calculation. Now, Boole had no idea that his work would be used to build computers. He was a pure mathematician and philosopher, interested in the structure of thought itself. He died in 1864 at the age of just 49, after walking to the university in heavy rain, developing pneumonia, and being treated by his wife with a method she believed in, pouring cold water over him while he lay in wet sheets, on the dubious theory that a cure should resemble its cause. He got worse and died. It's one of those stories that's almost too grim to be true, but it apparently is. Boole's work was admired by mathematicians but largely ignored by engineers. For almost 80 years, Boolean algebra sat in the pages of logic textbooks, a beautiful and seemingly impractical piece of abstract mathematics. And then, in 1937, a 21-year-old graduate student at MIT wrote a master's thesis that would change everything. His name was Claude Shannon, and what he realized, the connection he made, is one of those insights that seems obvious in retrospect, but that nobody had seen before. And it was simply this: electrical circuits can do Boolean logic. Think about a simple electrical switch. It's either open or closed, off or on, 0 or 1. Now think about two switches wired one after the other, in series. The current can only flow through if both switches are closed. Both must be on. That's an AND gate. Or wire them in parallel. The current flows if either switch is on. That's an OR gate. Add a switch that flips the signal. When it's supposed to be on, it turns off, and vice versa. That's a NOT gate. Shannon saw that every electrical relay circuit could be described using Boole's algebra, and conversely, that any logical expression in Boolean algebra could be built as an electrical circuit. Shannon's master's thesis, a symbolic analysis of relay and switching circuits, has been called the most important master's thesis of the 20th century, and it's hard to argue with that. In one stroke, he bridged the 80-year gap between Boole's abstract logic and the practical world of electrical engineering. He showed engineers that they could design circuits not by intuition and trial and error, but by writing down logical equations and translating them directly into wiring diagrams. And he showed that any computation that could be expressed in logic, which, as Boole had demonstrated, was all computation, could be carried out by electrical circuits. This is the moment when everything comes together. Leibniz's binary arithmetic, Boole's logical algebra, electrical switches that can be on or off. Shannon's proof that the three are the same thing. From here, building a computer is no longer a question of whether it's possible. It's a question of engineering. But before we follow the engineering, there's one more person we need to talk about, because he contributed the most important theoretical idea of all, the idea that made everything that came after it coherent. And he did it by imagining the simplest, most stripped-down computing machine conceivable, and then proving that this absurdly simple machine could compute anything that could ever be computed by anyone, ever. Alan Turing was born in London in 1912. His father was in the Indian Civil Service, which meant young Alan and his brother were largely raised in England by foster families and boarding schools while their parents were abroad. He was an unusual child, brilliant but socially awkward, fascinated by science and mathematics, not particularly good at the things English schools valued at the time, like classics and sports. He went to Sherborne School, and there, at the age of 15, he fell deeply in love with a fellow student named Christopher Morecambe. Christopher was also gifted in mathematics and science, and their friendship was intense and intellectually electric. Then, in February 1930, Christopher died suddenly of bovine tuberculosis. Turing was devastated. Some historians believe that Christopher's death shaped Turing's lifelong fascination with the nature of the mind, whether consciousness could survive the death of the body, whether a mind could exist in a machine. It's speculation, but it's poignant. Turing went to King's College, Cambridge, in 1931, and there he encountered a problem that had been gnawing at the foundations of mathematics. David Hilbert, the towering German mathematician, had posed what was called the Entscheidungsproblem, the decision problem. In plain language, the question was, does there exist a definite procedure, a step-by-step method that can determine whether any given mathematical statement is true or false. Hilbert believed the answer was yes. The dream was to mechanize mathematical reasoning itself, to build a truth machine. Now, by the time Turing got to it, part of the dream had already been shattered. In 1931, the Austrian logician Kurt Gödel had published his incompleteness theorems, showing that any mathematical system powerful enough to describe basic arithmetic would necessarily contain true statements that couldn't be proved within the system. Mathematics was inherently incomplete, but the question of whether there was still a general method for determining provability, a mechanical procedure for checking, remained open. Turing's approach was extraordinary. Instead of working purely in the abstract, he asked a concrete question. What does it actually mean to carry out a computation? What is a human doing when they sit at a desk and follow a set of rules to solve a problem? And to answer that, he imagined the simplest possible version of that activity. Picture an infinite strip of tape divided into squares. Each square holds a symbol, let's say a 0, a 1, or a blank. A reading head sits over one square. It can read the symbol, write a new symbol, and move one square left or one square right. It has a set of internal states. You can think of these as the machine's mood or mode, and a table of rules that says, if you're in this state and you read this symbol, then write this symbol, move in this direction, and switch to this state. That's it. That's the whole machine. It sounds almost laughably simple. A tape, a head, a table of rules. But here's the astonishing thing, and Turing proved it rigorously. This machine can compute anything that is computable. Any mathematical function, any algorithm, any computation that any computer has ever performed or will ever perform, can in principle be carried out by this simple device. It might take an absurdly long time. The tape might need to be absurdly long, but it can do it. There is no computation that requires more than this. And then Turing did something even more profound. He showed that you could build a universal Turing machine, a single machine that could simulate any other Turing machine. You'd simply encode the other machine's rules as symbols on the tape, feed them to the universal machine, and it would read those rules and carry out the computation. One machine, capable of becoming any machine, depending on what instructions you write on its tape. That's a stored program computer. That's the idea, and it's the most important idea in the history of computing, that the program is just data, that a machine doesn't need to be physically rebuilt for each new task. You just change the instructions. Turing published this in 1936 in a paper titled On Computable Numbers, with an application to the Entscheidungsproblem. He was 23 years old. The paper answered Hilbert's question. No, there is no general mechanical procedure for determining mathematical truth, and in the process, it laid down the theoretical blueprint for every computer that would ever be built. But theory and practice were about to collide in the most urgent way imaginable, because 3 years after Turing's paper, the world went to war. And the Second World War would do more to accelerate the development of actual, working computers than any other single event in history. Not because anyone set out to build a computer in the abstract, but because the military desperately needed to solve specific problems, cracking codes, calculating artillery trajectories, simulating nuclear explosions, and those problems demanded computational power that no army of human calculators could provide. Let's start with the codes, because that's where Turing himself ended up, and the story is extraordinary. In the 1920s and 1930s, the German military developed and adopted a family of encryption machines, the most famous of which was called Enigma. Enigma looked like a typewriter with some extra hardware on top. When you pressed a key, the electrical signal passed through a series of rotating wheels, rotors, each one wired to scramble the letters in a different way. After each key press, one or more rotors would advance, changing the scrambling. The number of possible configurations was staggering. The standard 3-rotor naval Enigma had something on the order of 159 million possible settings. If you didn't know the specific rotor configuration, the starting positions, and the plugboard settings, the encrypted message was, for all practical purposes, unbreakable by hand. The Poles actually made the first breakthroughs. A group of brilliant Polish mathematicians, Marian Rejewski, Jerzy Rosicki, and Henryk Zygalski, had been working on Enigma since the early 1930s, exploiting mathematical regularities in the machine's operation and building electromechanical devices to speed up the analysis. When war became imminent, in the summer of 1939, the Poles shared everything they had with the British and the French. It was an extraordinary act of intelligence cooperation, and it gave the British a crucial head start. Turing arrived at Bletchley Park, the British code-breaking center housed in a Victorian mansion in Buckinghamshire, in September 1939, the day after Britain declared war on Germany. He was 27 years old, and over the next several years, he became the intellectual driving force behind the effort to break Enigma on a daily basis, not just cracking the code once, but breaking each day's new settings fast enough for the intelligence to be useful. He designed an electromechanical device called the bomb, building on the earlier Polish work, that could rapidly test possible Enigma configurations by exploiting logical contradictions in the encrypted messages. The Bombays were big, noisy, impressive machines, about the size of a large wardrobe, full of rotating drums that simulated the Enigma's rotors, and at their peak, more than 200 of them were running around the clock at Bletchley Park and its outstations. The intelligence produced by breaking Enigma, known as Ultra, is widely credited with shortening the war by at least 2 years. Historians debate the exact impact, but the consensus is that Ultra gave the Allies a decisive advantage in the Battle of the Atlantic, the North Africa campaign, the D-Day planning, and numerous other critical moments. Turing's contribution was essential, and it was kept secret for decades after the war. He received an OBE in 1946, but the citation was vague, and nobody outside the intelligence community knew what he'd actually done. But for our story, what matters most about Bletchley Park is what was being built in the buildings next door. Because while Turing was working on Enigma, the Germans were also using a different, more sophisticated encryption system for their highest-level communications, messages between Hitler and his generals, the really critical stuff. This system used a machine called the Lorenz cipher, which was significantly more complex than Enigma, and to break it, the British built something that took computing into a fundamentally new territory. It was called Colossus, and it was designed primarily by Tommy Flowers, a post office telephone engineer who had been working with electronic switching equipment. Colossus used vacuum tubes, the same kind of glass bulbs that powered early radios and televisions, as its switching elements, instead of the mechanical relays used in the Bombays. A vacuum tube can switch on and off thousands of times per second, compared to a relay's clicks, which were limited to maybe 10 or 20 times a second. The first Colossus, operational in early 1944, used about 1,500 vacuum tubes. The improved Mark II version, rushed into service just before D-Day, used 2,400. Colossus was not a general-purpose computer. It was built specifically for code breaking, specifically for the Lorenz problem. But it was programmable in a limited sense. You could change its configuration using switches and plug boards to tackle different aspects of the analysis. And it was electronic. That's the key word. It used vacuum tubes rather than mechanical parts for its core logic. It was blazingly fast by the standards of the day, processing characters from the encrypted message at 5,000 characters per second. And it was kept so secret that its existence wasn't officially acknowledged until the mid-1970s, and the full details of its design weren't released until the 2000s. Tommy Flowers was ordered to destroy the Colossus machines and all their documentation after the war. He did, and spent years unable to tell anyone what he'd accomplished. Meanwhile, across the Atlantic, a different kind of computing project was underway, driven by a different military need. The United States Army needed to calculate artillery firing tables, charts that told gunners how to aim their weapons based on distance, elevation, wind speed, temperature, and dozens of other variables. Each table required thousands of individual trajectory calculations, and each trajectory calculation involved solving complex differential equations, which took a human computer about 20 hours of handwork. By 1943, the Army's Ballistic Research Laboratory at Aberdeen Proving Ground was falling further and further behind. New weapons were being deployed faster than the firing tables could be computed. The solution was ENIAC, the Electronic Numerical Integrator and Computer, built at the University of Pennsylvania by John Moschly and J. Presper Eckert. ENIAC was a colossus of a different kind. It used over 17,000 vacuum tubes, weighed about 30 tons, occupied an entire room, and consumed about 150 kilowatts of power. When it was running, legend has it that the lights in nearby parts of Philadelphia dimmed. That's probably an exaggeration, but not by much. It generated so much heat that massive cooling systems were needed, and the tubes burned out constantly. Finding and replacing dead tubes was a full-time job, but when it worked, it was staggeringly fast. It could perform 5,000 additions per second, which was roughly 1,000 times faster than any electromechanical calculator in existence. ENIAC ran its first major calculation in December 1945. And here's an interesting detail. That first calculation wasn't an artillery table. It was a simulation for the hydrogen bomb program at Los Alamos. The machine had been co-opted for an even more urgent military application before it could start on its original purpose. It ran continuously for months, gobbling up calculations that would have taken years by hand. Now, ENIAC had a significant limitation. It was programmed by physically rewiring its circuits. To set up a new problem, you had to rearrange cables, flip switches, adjust function tables, a process that could take days. The machine itself was fast, but the setup was slow and laborious. And this is where another key figure enters the story, the Hungarian-born mathematician John von Neumann, who may have been the most brilliant mind of the 20th century, and who contributed an idea to computing that remains the basis of virtually every computer built today. Von Neumann learned about ENIAC during a chance encounter at a train station. He met Hermann Goldstein, one of the Army's liaisons to the project, on a train platform at Aberdeen in the summer of 1944, and became fascinated. He joined the project as a consultant and quickly grasped both the machine's power and its fundamental limitation. The problem was that the program, the sequence of instructions, was physically separate from the data. The instructions were wired in, while the data was loaded into the machine's accumulators. Changing the program meant physically reconfiguring the machine. Von Neumann's insight, which he outlined in a famous 1945 draft report on a proposed successor machine called EDVAC, was that the program should be stored in the same memory as the data. This is the stored program concept, and even though Turing had described the principle theoretically in 1936 with his universal machine, von Neumann was the first to lay out a practical architecture for it. In what's now called the von Neumann architecture, a computer has a processing unit that fetches instructions from memory, decodes them, and executes them, one after another. The instructions are just numbers stored in memory, exactly like the data they operate on. This means you can change the program just by loading different numbers into memory. No rewiring, No reconfiguration, just new data. This architecture, a central processing unit, memory that holds both program and data, and input-output mechanisms, is still, in its essential form, how virtually every computer works today. Your laptop, your phone, the servers running the internet, the computer in your car, they're all von Neumann machines. The details have changed enormously. The speeds are incomprehensibly faster. But the fundamental structure is the one von Neumann described in 1945. It's one of those ideas that's so successful, so foundational, that it becomes invisible. You don't notice the architecture any more than you notice the grammar of your native language. It's just how things are done. And by the late 1940s, several groups were racing to build the first stored program computers. The first to get there was a team at the University of Manchester, in England, who in June 1948 ran the first program on a machine called the Manchester Baby, a small experimental computer that used cathode ray tubes for memory and could store just 32 words of 32 bits each. The Baby's first program, written by Tom Kilburn, was designed to find the highest proper divisor of a number. It ran for 52 minutes, trying over 3 million different possibilities, and produced the correct answer. It was a modest computation by any modern standard, but it was the first time in history that a computer had run a program stored in its own electronic memory. The age of the modern computer had begun. But to understand what was actually happening inside those early machines, what a vacuum tube was actually doing, and why it mattered so much, and why vacuum tubes would soon be replaced by something far better, we need to talk about what switches really are and how electricity can be made to carry logic. Because that's really the heart of the whole thing. Everything we've talked about so far, binary numbers, Boolean logic, Shannon's insight, the Turing machine, the von Neumann architecture, it all converges on one physical question. What kind of switch should you use? Let's go back to vacuum tubes for a second, because understanding how they work will help you understand everything that comes after. A vacuum tube, at its most basic, is a glass bulb with the air pumped out and some metal parts sealed inside. The simplest kind, called a diode, has two elements, a cathode and an anode. The cathode is a piece of metal that's heated up, usually by a filament, like the glowing wire in an old incandescent light bulb. When the cathode gets hot enough, electrons start boiling off its surface. That's called thermionic emission, and it's a real thing. Heat a metal enough, and electrons literally escape from it, like steam rising from boiling water. Now, if you put a positively charged plate, the anode, nearby, those freed electrons are attracted to it, and current flows through the tube. But if the anode is negatively charged, the electrons are repelled, and no current flows. So the tube acts as a one-way valve for electricity. Current can flow from cathode to anode, but not the other way. That's a diode. But the really useful vacuum tube is the triode, which adds a third element, a wire grid, literally a fine mesh of wire placed between the cathode and the anode. And here's the clever part. By applying a small voltage to that grid, you can control the flow of a much larger current between the cathode and the anode. A small negative voltage on the grid repels the electrons streaming from the cathode, reducing the current. Make the grid voltage negative enough, and the current stops entirely. The tube switches off. Remove the negative voltage, and the current flows again. The tube switches on. A tiny signal controls a big signal. That's amplification. And it's also switching. This is why vacuum tubes could be used as computing elements. A triode can be on or off, controlled by an electrical signal. On represents 1. Off represents 0. Wire a few tubes together the right way, and you've got a logic gate, an AND gate, an OR gate, a NOT gate. The same Boolean operations that Shannon had shown could be built from switches, and tubes could switch thousands of times per second. far faster than any mechanical relay. But tubes were terrible in other ways. They were big, each one roughly the size of your thumb, and you needed thousands of them for a useful computer. They consumed enormous amounts of power, mostly as heat. Those glowing filaments were burning energy just to keep the cathodes hot enough for thermionic emission. They were unreliable. The filaments burned out, just like light bulbs, and with 17,000 tubes in ENIAC, the average time between failures was measured in hours or days. The machines needed constant maintenance, air conditioning, backup tubes, and technicians who could diagnose which of thousands of identical glass bulbs had gone dark. Everyone knew tubes were a temporary solution. They worked, but they were a bottleneck. The future of computing depended on finding something better, something smaller, cooler, more reliable, and faster. And that something was being born right around the same time that ENIAC was blinking and humming in Philadelphia, in a research laboratory in Murray Hill, New Jersey. The place was Bell Telephone Laboratories, and the device was the transistor. The transistor story starts with a material, silicon, or more precisely, the class of materials called semiconductors. And to understand why the transistor works, you need to understand what a semiconductor is, because this is truly the foundation of the entire digital world, and it's one of those things that's both simple and profound at the same time. You probably know that some materials conduct electricity well, metals like copper and gold, for instance. The electrons in these materials are loosely bound to their atoms, free to move around, forming a kind of electron sea that can carry current easily. That's a conductor. And some materials barely conduct at all: glass, rubber, most plastics. The electrons are tightly bound, stuck in place, no current flows. That's an insulator. But semiconductors are the Goldilocks materials. They sit in between. They're not great conductors and not great insulators. They're in the middle. Silicon is the most famous semiconductor, and it's the basis of almost every computer chip ever made. Pure silicon forms a crystalline structure, where each silicon atom bonds with 4 neighbors, sharing electrons in a stable lattice. In pure silicon at room temperature, almost all the electrons are locked in bonds, so it's a poor conductor. Not much current flows. But here's where it gets interesting. If you add a tiny amount of a different element, a process called doping, you can dramatically change silicon's electrical properties. Let's say you take a crystal of pure silicon and mix in a tiny amount of phosphorus. Phosphorus has 5 outer electrons, while silicon has 4. So when a phosphorus atom takes a silicon atom's place in the crystal, 4 of its electrons bond with the surrounding silicon atoms, but the 5th one is left over, only loosely attached. It doesn't take much energy to knock that 5th electron free, and once it's free, it can carry current. You've created a material with extra free electrons, negatively charged carriers. This is called N-type silicon, where the N stands for negative, because the free carriers are negatively charged electrons. Now do the opposite. Dope the silicon with boron instead. Boron has only 3 outer electrons. When it replaces a silicon atom in the lattice, it can only form 3 bonds, leaving a gap, a missing electron in the crystal structure. That gap is called a hole, and it behaves like a positive charge carrier. When an electron from a neighboring bond jumps into the hole, it fills it, but it leaves a new hole behind where it came from. The hole effectively moves through the crystal, and it acts like a positive charge flowing in the opposite direction of the electrons. This is P-type silicon, P for positive. Here's the thing that makes this matter. When you put a piece of N-type silicon next to a piece of P-type silicon, something remarkable happens at the boundary. The junction. The free electrons from the N side drift across and fill some of the holes on the P side. This creates a thin zone at the junction, called the depletion region, where there are no free carriers, and a small built-in electric field that resists further flow. If you apply voltage in one direction, positive to the P side, it overcomes the built-in field and current flows freely. Apply it the other direction, and the depletion region gets wider, blocking current. You've made a diode, a one-way valve for electricity, but out of a tiny piece of doped silicon instead of a big glass vacuum tube. And now for the key step. A transistor takes this one step further. The most common type, called a bipolar junction transistor, or BJT, is essentially a sandwich, NPN, or PNP. 3 layers of doped silicon, with the thin middle layer being the opposite type from the 2 outer layers. The 3 layers are called the emitter, the base, and the collector. And the magic is this. By applying a small current to the thin base layer, you control a much larger current flowing between the emitter and the collector. A tiny signal controls a big one. Sound familiar? It's the same principle as the vacuum tube's grid, but achieved with a sliver of silicon instead of a heated glass bulb. No filament, no vacuum, no glass envelope, no heat-wasting thermionic emission. A transistor can be made incredibly small. The first ones, in 1947, were built by hand and were about the size of a pencil eraser, but they quickly shrank, and today the transistors in your phone are measured in nanometers, billionths of a meter, smaller than a virus. They switch in picoseconds, trillionths of a second. They consume almost no power compared to tubes, and they're astonishingly reliable. A modern transistor can switch trillions of times without wearing out. The transistor was invented at Bell Labs on December 23, 1947. The key people were 3 physicists, William Shockley, John Bardeen, and Walter Brattain. The story is fascinating and messy, full of human drama. Shockley was the team leader, brilliant and abrasive, with a massive ego and a gift for theoretical insight. Bardeen was quieter, a theorist of extraordinary depth. He remains, to this day, the only person ever to win 2 Nobel Prizes in physics. Brattain was the experimentalist, the one with the steady hands and the intuition for making things work in the lab. Shockley had been pushing for a semiconductor amplifier since the late 1930s, but his early designs didn't work, and he couldn't figure out why. It was Bardeen who supplied the crucial theoretical insight. He proposed that there were surface states on the semiconductor that were trapping charges and preventing the device from functioning as Shockley predicted. And it was Bardeen and Brattain together, working intensely through November and December of 1947, who built the first working transistor, the point contact transistor. It was a crude device, 2 closely spaced gold contacts pressed against a tiny slab of germanium, another semiconductor, but it worked. It amplified an electrical signal. When they demonstrated it to Shockley and other Bell Labs researchers on December 23rd, the room fell quiet. Everyone knew what it meant. What happened next was ugly. Shockley was furious that Bardeen and Brattain had achieved the breakthrough largely without him. He felt that his earlier theoretical work had laid the groundwork, and he was determined to reclaim credit. He threw himself into developing a better design, and within a few weeks, he had invented the junction transistor, the NPN sandwich I described earlier, which was more reliable and more practical than the point contact type. This became the basis for the semiconductor industry. All 3 shared the Nobel Prize in Physics in 1956, but the personal fallout was severe. Bardeen left Bell Labs in 1951, partly because of the toxic dynamic with Shockley. And Shockley's later career took a dark and disturbing turn. He founded a semiconductor company in Palo Alto in 1956, hired brilliant young engineers, managed them so badly that 8 of them quit to found their own company, Fairchild Semiconductor, which would later spawn Intel and much of Silicon Valley. Shockley himself veered into promoting racist theories about intelligence and genetics, becoming increasingly isolated and widely condemned. He died in 1989, largely estranged from his own children. The man who co-invented the transistor, arguably the most important invention of the 20th century, spent his last decades in bitterness and disgrace. It's a strange and cautionary tale, but the transistor itself changed the world. It changed the world because it gave engineers a switch that was small, fast, reliable, and cheap. And with a small, fast, reliable, cheap switch, you could build everything that Shannon and Turing and von Neumann had theorized. You could build logic gates. You could build memory circuits. You could build processors. You could build computers. And unlike vacuum tube computers, which filled rooms and required teams of technicians, transistor computers could be smaller, cooler, more reliable, and eventually, small enough and cheap enough for ordinary people to own. But before the transistor could truly transform computing, one more revolution was needed. A revolution in how you put transistors together. Because in the 1950s, even though transistors were smaller than vacuum tubes, building a complex circuit still meant wiring together thousands of individual components by hand. Transistors, resistors, capacitors, diodes, all connected with wires soldered one at a time. It was painstaking, expensive, and error-prone. The more complex the circuit, the more connections, and the more connections, the more chances for something to fail. This was called the tyranny of numbers, and it was the biggest bottleneck in electronics. The solution came from two people, working independently, at almost the same time, in one of those coincidences that history occasionally delivers. And the solution was to stop building circuits from separate components, and instead build the entire circuit, transistors, resistors, wires, everything, on a single piece of semiconductor material. One tiny chip, everything integrated. They called it the integrated circuit, and it would become the most manufactured object in human history. The first person to demonstrate one was Jack Kilby, a newly hired engineer at Texas Instruments in Dallas. It was the summer of 1958, and Kilby was one of the few employees who didn't yet have vacation time accrued. So while most of the company was away, he was alone in the lab, thinking about the interconnection problem. His idea was radical. Instead of wiring together separate components, what if you fabricated all the components from the same block of semiconductor material? Transistors, resistors, even capacitors, all carved from a single piece of germanium. On September 12, 1958, Kilby demonstrated his integrated circuit to Texas Instruments management. It was a rough-looking thing, a small germanium chip with tiny gold wires bonded to it by hand. But it worked. A complete circuit on a single piece of semiconductor. About 6 months later, Robert Noyce at Fairchild Semiconductor, one of those 8 engineers who had defected from Shockley's company, independently came up with the same basic idea, but with a crucial improvement. Noyce used the planar process, a manufacturing technique developed by his colleague Gene Hoerni, which deposited components on the surface of a flat silicon wafer and connected them with thin metal traces printed directly on the chip. No hand-wired connections. Everything was deposited and etched using photographic techniques, which meant it could be mass-produced. Noyce's version was more practical, more scalable, and ultimately became the basis for the entire semiconductor industry. Both Kilby and Noyce are credited as co-inventors of the integrated circuit. Kilby received the Nobel Prize in Physics in 2000 for it. Noyce had died in 1990 and couldn't share the award. Their invention didn't just improve computing, it created the modern world. Here's why. Once you can build an entire circuit on a single chip, you can make it smaller. And once you start making it smaller, something remarkable happens. Smaller transistors switch faster, use less power, and cost less to manufacture, because you can fit more of them on each wafer. So there's a virtuous cycle. Smaller is better in every way. And the semiconductor industry embarked on a decades-long sprint to make things smaller and smaller, cramming more and more transistors onto each chip. In 1965, Gordon Moore, another Fairchild alumnus who would co-found Intel with Noyce, noticed a pattern. The number of transistors on a chip was roughly doubling every year or two. He predicted this trend would continue, and it did, for decade after decade. This became known as Moore's Law, and it's one of the most remarkable trends in the history of technology. In 1971, Intel's first microprocessor, the 4004, had 2,300 transistors. By the mid-1980s, that number was in the hundreds of thousands. By the late 1990s, tens of millions. Today, the chips in a modern smartphone contain something like 15 to 20 billion transistors. Each one of those transistors is just a few nanometers across. For perspective, a human hair is roughly 80,000 nanometers thick. You could line up tens of thousands of modern transistors across the width of a single hair. But I want to slow down here, because we've been talking a lot about the history and the hardware, and I haven't yet explained the thing that ties it all together, the thing that makes the whole machine actually work. How does a computer actually compute? What is happening, step by step, when your phone adds two numbers, or loads a web page, or plays a song? How do switches that are merely on or off produce the entire digital world? Let's go from the bottom up. Start with a single transistor, on or off, 1 or 0. That's a single binary digit, a bit. 1 bit isn't much. It can represent two states, yes or no, true or false, on or off. But take 8 bits and group them together. That's a byte. 8 binary digits, each independently 0 or 1. How many different patterns can you make with 8 bits? 2 to the power of 8, which is 256. So a byte can represent any of 256 different values. You could map those values to letters of the alphabet, and that's exactly what we do. There's a standard code called ASCII that assigns a number between 0 and 127 to each common character. The capital letter A is 65, which in binary is 01000001. The lowercase a is 97, 011000001. The space character is 32, 001000. Every text message you've ever sent was encoded like this, character by character, each one translated into a pattern of ones and zeros, each one stored as a specific configuration of switches inside a chip. Now, representing numbers in binary is straightforward. Our familiar decimal system is base 10. Each position represents a power of 10. The number 237 means 2 hundreds, 3 tens, and 7 ones. Binary is the same idea, but base 2. Each position represents a power of 2. The binary number 1101 means 1814, 02s, and 11, which adds up to 13. Any number, no matter how large, can be written in binary. It's just longer. The number 237 in binary is 111, 8 digits instead of 3. But that's fine, because switches are cheap and fast. You don't mind using more of them. Here's where Boolean logic comes back, because this is where the magic happens. Remember and, or, and not? Those aren't just abstract logical operations. They're physical circuits made from transistors. Let me show you how an AND gate works at the transistor level. Take 2 transistors and wire them in series, one after the other. The output of the gate is the signal coming out the far end. For current to flow through both transistors and produce an output, both transistors need to be switched on. If either one is off, no current flows. and the output is 0. Both on. Both inputs are 1. Output is 1. That's AND. It's the physical incarnation of Boole's multiplication of zeros and ones, built from the transistor that Bardeen and Brattain demonstrated in that Bell Labs room in 1947, using the connection that Shannon saw in 1937. The whole chain of ideas is right there, in a couple of transistors wired together. An OR gate uses transistors in parallel instead of series. If either transistor is on, current can flow through that path, and the output is 1. A NOT gate, also called an inverter, uses a single transistor in a configuration where a high input signal produces a low output, and vice versa. It flips the bit. And here's the beautiful thing. With just these 3 types of gates, you can build any logical or arithmetic operation, any computation. Shannon proved this in his thesis, and Turing proved it in his paper. But let me show you how it works in practice. Let's build a circuit that adds 2 single-digit binary numbers. Adding in binary is simpler than in decimal. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is, well, in binary, 1 plus 1 is 10, which means 0 with a carry of 1, like how 9 plus 1 in decimal gives you 0 with a carry. So to add 2 single bits, you need a circuit with 2 outputs, the sum and the carry. If you work through the truth table, all 4 combinations of 2 input bits, you find that the sum is produced by an XOR gate, which is a gate that outputs 1 if the inputs are different and 0 if they're the same. And the carry is produced by an AND gate. You only carry when both inputs are 1. That little circuit, 1 XOR gate and 1 AND gate, is called a half adder. It adds 2 single bits. Now, to add multi-bit binary numbers, you need to handle the carry from each column. So you chain together slightly more complex circuits called full adders, each one taking 3 inputs, 2 bits to add, plus the carry from the previous column, and producing a sum bit and a carry bit. String 8 full adders together, and you have an 8-bit adder. Feed it 2 8-bit binary numbers, and it produces the 8-bit sum, plus a carryout for overflow. This entire circuit is built from nothing but AND, OR, NOT, and XOR gates, which are themselves built from transistors. Addition, the most fundamental arithmetic operation, emerges from switches, and multiplication, it's just repeated addition with shifting, which you can also build from gates. Subtraction, you can do it by flipping bits and adding, a trick called 2's complement that's incredibly elegant. Division, more complex, but still reducible to gates. Everything is gates. Everything is switches. Everything is ones and zeros. Now, a real computer doesn't just do one operation. It does millions of them in sequence, one after another, following a list of instructions. And the component that does this, the heart of the whole machine, is called the Central Processing Unit, or CPU. And at its core, the CPU does something remarkably simple. It follows a cycle: fetch, decode, execute, over and over, billions of times per second. Here's how it works. The CPU has a register called the program counter, just a small piece of memory that holds the address of the next instruction. The CPU fetches that instruction from memory, pulls it in, reads the binary pattern, then it decodes the instruction, figures out what operation it's asking for. Add these 2 numbers, move data from here to there, compare 2 values, jump to a different instruction if some condition is true. The decoding circuitry interprets the binary pattern and sends the right signals to the right parts of the processor. Then the CPU executes the instruction. The arithmetic unit does the math, or data moves between registers, or the program counter is updated to point somewhere else. And then the cycle repeats. Fetch the next instruction. Decode it. Execute it. Fetch. Decode. Execute. That's it. That's what a computer does. A modern CPU does this billions of times per second. A processor running at 3 GHz is completing roughly 3 billion fetch, decode, execute cycles every second. And each instruction is simple. Add 2 numbers, compare a value, move some data, store a result. No single instruction does anything impressive on its own. But 3 billion per second, following a carefully crafted sequence, that produces everything. And this is the deep lesson of computing. The thing that I think is genuinely beautiful about it. Computers don't work because they do anything complicated. They work because they do something incredibly simple, incredibly fast, in incredibly long sequences. Complexity emerges from simplicity. The richness of the digital world, every streaming movie, every video game, every medical scan, every weather forecast, every financial transaction, all of it is built from binary switches performing Boolean operations under the control of stored programs, executing the fetch, decode, execute cycle. The entire tower of modern technology rests on this foundation. A switch that can be on or off. But a CPU is useless without memory, somewhere to store the instructions and the data. And computer memory is a story in itself, a story of cleverness and trade-offs. Because what you really want is memory that's fast, large, cheap, and persistent, that holds its data even when the power goes off. And it turns out you can have some of those things, but not all of them at once. So computers use a hierarchy of different memory types, each one a different compromise. At the very fastest level, closest to the CPU, there are registers, tiny, incredibly fast storage locations built right into the processor. A modern CPU might have a few dozen registers, each one holding just one number. They're the scratch pad, the working memory that the CPU uses during each instruction. Below that comes cache memory, small but fast memory, also built into the processor chip, that stores recently accessed data and instructions on the assumption that they'll probably be needed again soon. This is called temporal locality, and it works surprisingly well. Programs tend to access the same data over and over in tight loops. Cache is measured in megabytes. Your computer probably has a few megabytes of cache spread across several levels, called L1, L2, and L3, each one larger but slightly slower than the one above. Below cache comes main memory, what's usually called RAM, random access memory. This is the big pool of working memory that your applications actually use. When you open a program, its instructions are loaded from the hard drive into RAM. When you're editing a document, the document is sitting in RAM. Modern computers have anywhere from a few gigabytes to dozens of gigabytes of RAM, and it's fast. It can deliver data to the CPU in nanoseconds, billionths of a second. But RAM is volatile. When you turn off the power, everything in RAM vanishes. The data isn't stored permanently, which is why you have to save your work. And at the bottom of the hierarchy, there's storage, hard drives or solid-state drives. This is where data lives permanently, even when the power is off. A solid-state drive stores data using a special kind of transistor called a floating-gate transistor, which traps electrons in an insulated pocket where they can sit indefinitely without power. It's essentially using the quantum mechanical properties of an insulating barrier to keep electrons imprisoned. A tiny charge, locked in place, representing a 1 or a 0. It's slower than RAM, but it's persistent and it's cheap, and you can fit terabytes of data on a chip the size of a postage stamp. So your computer is constantly shuffling data up and down this hierarchy, pulling things from slow, permanent storage into fast, temporary RAM, caching the most frequently used data in even faster cache, and finally working with it in the blazing fast registers right inside the CPU. The whole system is designed to feed the processor fast enough to keep those billions of fetch decode execute cycles humming along without stalling. It's an intricate dance, and it's happening right now, in every computer on the planet, millions of times per second, without you ever noticing. And all of this, the transistors, the gates, the adders, the CPU, the memory hierarchy, all of this is just the hardware. It's the machine. But a computer without software is like a brain without thoughts. The hardware can execute instructions, but someone has to write those instructions. Someone has to tell the machine what to do. And the story of how we went from flipping switches and rewiring cables to the software you tap on your screen every day is its own fascinating evolution. A story of abstraction, piled on abstraction, until the underlying machinery almost disappears entirely. In the very beginning, programming meant working directly in the machine's own language, machine code, raw binary. Every instruction was a specific pattern of ones and zeros, and programmers had to know exactly what each pattern meant. Load this value into this register. That's one pattern. Add the contents of 2 registers. Another pattern. Store the result in this memory location. Another. Each processor had its own set of instructions, its own binary codes, its own peculiarities, and programming in machine code was exactly as tedious and error-prone as it sounds. A single wrong bit, a 0 where there should have been a 1, could crash the entire program, or worse, produce wrong answers that looked right. There were no safety nets, no helpful error messages, no undo buttons. The first step up from that was assembly language, which appeared in the early 1950s. Instead of writing raw binary, you'd write short mnemonic codes, ADBA for addition, MOV for moving data, JMP for jumping to a different instruction. A program called an assembler would then translate those mnemonics into the actual binary machine code. It sounds like a small improvement, but it was transformative. Suddenly, you could read a program and have some idea what it was doing. ADD R1, R2 was a lot more meaningful than 000000000010000000100000001 0000001. The logic was the same, but the representation was human-readable. But assembly language was still tied to a specific processor. A program written in assembly for one type of machine couldn't run on a different type. You'd have to rewrite it from scratch, and it was still painfully detailed. Every tiny operation had to be spelled out. If you wanted to compute something as simple as the average of a list of numbers, you'd need dozens of instructions. Loading values, maintaining a running sum, counting elements, dividing, handling memory addresses, managing loop counters. The programmer had to think like the machine, keeping track of registers and memory addresses, and the exact sequence of every operation. The breakthrough came with high-level programming languages, and the person who did more than anyone to make them possible was Grace Hopper. Hopper is one of the most remarkable figures in the history of computing, and she deserves a long look. She was born in New York City in 1906. She studied mathematics and physics at Vassar, earned a PhD in mathematics from Yale, and joined the Navy during World War II, where she was assigned to work on the Harvard Mark I, one of the earliest electromechanical computers. She fell in love with computing and never left. In the early 1950s, Hopper had an idea that most of her colleagues thought was crazy. She proposed building a program, she called it a compiler, that would take instructions written in something close to English and automatically translate them into machine code. You'd write something like multiply price by quantity, and the compiler would figure out which registers to use, which machine instructions to generate, how to manage the memory. The programmer could think about the problem, not the machine. When she first proposed it, people literally told her that computers couldn't do that. Computers do math, they said. They don't understand English. And Hopper's answer was beautiful in its directness. She said something along the lines of, "I already have a working compiler. Nobody would believe it was possible, so I just went ahead and built it." Her first compiler, called A0, was operational in 1952. It was rudimentary by modern standards, but it proved the concept. And it led, through several iterations, to the development of COBOL, the Common Business-Oriented Language, in the late 1950s, designed to be readable, portable, and usable by people who weren't mathematicians. COBOL was so successful that it's still running today, decades later, in banks and government systems around the world. Meanwhile, John Backus at IBM led the development of Fortran, formula translation, in 1957, designed for scientific and engineering computation. Fortran let scientists write mathematical formulas in a notation close to standard algebra, and the compiler translated them into efficient machine code. It was astonishingly popular and remained the dominant language for scientific computing for decades. What compilers did was create a layer of abstraction. The programmer no longer had to think about the hardware. They could express their ideas at a higher level, and the compiler would handle the messy details of translation. This was a profound shift, and it established a pattern that would repeat over and over in the history of computing. Each new layer hides the complexity below it and provides a simpler interface above it. Assembly hides machine code. High-level languages hide assembly, and the layers kept stacking. Here's why abstraction matters so much. Think about what happens when you tap a letter on your phone's keyboard. Just one letter. Say, the letter A. What actually happens? Your finger touches the glass screen. The screen is a capacitive touch screen, which works by detecting changes in an electrical field. Your finger, being slightly conductive because of the moisture in your skin, distorts the electric field at the point of contact. The touchscreen controller, a small chip built into the phone, detects which region of the screen was touched and sends the coordinates to the processor. The processor is running the operating system, which is a massive piece of software that manages everything: the screen, the memory, the apps, the networking, the battery, 100 other things. The operating system receives the touch coordinates, figures out which app is in the foreground, and sends a touch event to that app. The app, say it's a text editor, receives the event, looks up which key on the virtual keyboard corresponds to those coordinates, determines that it's the letter A, adds the letter A to the text buffer, and tells the display system to redraw the screen with the new letter. Now, drawing that letter on screen means the app has to tell the graphics system which pixels should change color. The letter A is represented as a shape, a vector outline, or a bitmap font, and the graphics system has to rasterize it, meaning convert the shape into a grid of pixels. Each pixel has a color value, typically described by 3 numbers: the intensity of red, green, and blue, each ranging from 0 to 255, which means each pixel uses 3 bytes, or 24 bits. The graphics system writes these pixel values into a region of memory called the frame buffer. The display controller reads the frame buffer and sends the appropriate signals to the screen, which uses millions of tiny LEDs or liquid crystal elements, one for each subpixel, to physically produce the light that enters your eyes. And all of this, the touch detection, the coordinate lookup, the event dispatch, the character mapping, the font rendering, the pixel rasterization, the frame buffer write, the display update, happens in a fraction of a second. You tap, the letter appears. It feels instant. It feels simple. But underneath, thousands of software layers are working together, and millions of transistors are switching, and data is flowing through the memory hierarchy, and the CPU is cycling through fetch, decode, execute millions of times, all to put one letter on your screen. That's the power of abstraction. The programmer who wrote the text editor doesn't think about pixels. They think about characters and text buffers. The programmer who wrote the graphics system doesn't think about individual transistors. They think about pixel values and rendering algorithms. The hardware designer who laid out the CPU doesn't think about apps. They think about logic gates and timing. Each layer does its job, trusts the layers below it to do theirs, and presents a clean interface to the layers above. It's like a city. You turn on the faucet and water comes out, and you don't have to think about the reservoir, the treatment plant, the pipes under the street, the pump stations, the chemical dosing. Someone does, but it doesn't have to be you. Computers are built the same way, layer upon layer of organized complexity, each one hiding the details of the one below. And sitting at the center of all these layers, managing everything, is the operating system. The operating system is the master coordinator. It decides which program gets to use the CPU and for how long. It manages memory, making sure different programs don't interfere with each other's data. It handles input and output, keyboards, mice, touchscreens, speakers, network connections, storage drives. It provides services that applications rely on, like file systems and security and scheduling. The idea of an operating system emerged in the 1950s and 60s as computers became fast enough to handle more than one task. Early computers ran one program at a time. You loaded it, ran it, waited for results, loaded the next one. But the CPU was often idle, waiting for slow operations like reading from tape or printing output. A brilliant insight at places like MIT and Bell Labs was that the computer could be doing something else while it waited, running a different program, or a different part of the same program. This idea, time sharing, led to systems like Multics in the 1960s, and then, crucially, to Unix. Unix was created at Bell Labs starting in 1969 by Ken Thompson and Dennis Ritchie. Thompson, the story goes, had been working on the Multics project, which was ambitious but unwieldy. When Bell Labs pulled out of Multics, Thompson found himself with ideas but no computer. He discovered an unused PDP-7 minicomputer in a hallway and started building a simpler, leaner operating system from scratch. Ritchie joined him, and together they created something elegant and influential. Unix introduced ideas that are now so standard they feel inevitable. A hierarchical file system, pipes that let you chain small programs together. A design philosophy of small, modular tools that each do one thing well. Dennis Ritchie also created the C programming language, initially just as a tool for rewriting Unix in a portable language. C was a remarkable language, close enough to the hardware to be efficient, high level enough to be productive, and clean enough to be portable across different types of processors. Unix, rewritten in C, could run on different machines with minimal modification, which was revolutionary. The combination of Unix and C spread through universities and research labs in the 1970s and 80s, and their descendants are everywhere today. Linux, which powers most of the world's servers, most Android phones, and virtually all of the cloud infrastructure you interact with daily, is a direct descendant of Unix. macOS and iOS are built on a Unix foundation too, and C begat C++, which influenced Java, which influenced C#, and on and on. The family tree of programming languages is tangled and fascinating, but C sits near the root of all of it. But let me pull back for a second, because I want to make sure something is clear, because it's easy to lose in all these layers of technology. Everything we've been talking about, every programming language, every operating system, every app, every algorithm, every piece of software ever written, is, at the end of the day, a sequence of instructions that gets translated, layer by layer, down through compilers and assemblers and operating system calls, until it reaches the hardware level, where it becomes patterns of ones and zeros being fed to a CPU that fetches, decodes, and executes them, one at a time, billions of times per second, using logic gates built from transistors etched into silicon. The whole tower of abstraction, from the fanciest app to the simplest gate, is connected by this unbroken chain. The app says, "Display this photo." The graphics library says, "Draw these pixels." The operating system says, "Write these bytes to the frame buffer." The CPU says, "Load, add, store, branch." The transistors say on, off, on, off, and the photo appears on your screen. That chain is what a computer is. It's not magic, though it can feel like it. It's engineering. Layers of clever, careful, sometimes breathtakingly elegant engineering, built up over decades by thousands of people who each solved one piece of the puzzle. And the thing that makes it all possible, the reason the whole tower stands, is that the bottom layer, the switches, the logic gates, the basic Boolean operations, is absolutely, perfectly, mathematically reliable. A gate that should output a 1 always outputs a 1. A gate that should output a 0 always outputs a 0. The certainty of logic built into silicon gives you a foundation solid enough to stack everything else on top of. And that brings us to something I haven't talked about yet, something that transformed computers from isolated calculating machines into the interconnected world you live in. Because for the first few decades of computing, computers were islands. They sat in their climate-controlled rooms, doing their calculations, and if you wanted to move data between two computers, you physically carried a tape or a disk from one to the other. There was a joke about this. Never underestimate the bandwidth of a station wagon full of magnetic tapes. But starting in the late 1960s, people began to ask a question that would change civilization. What if computers could talk to each other? The answer began, like so many transformative technologies, with the military. In 1962, a psychologist and computer scientist named J.C.R. Licklider, who went by the nickname Lick, joined the Advanced Research Projects Agency, ARPA, which was the Pentagon's research funding arm, created in response to the shock of Sputnik. Licklider had a vision he called the Intergalactic Computer Network, a deliberately grandiose name for the idea that computers at different research institutions should be connected so they could share data and resources. It wasn't an entirely new idea, but Licklider had the funding, the influence, and the persuasive power to make it happen. The technical challenge was formidable. How do you send data reliably between two computers that might be thousands of miles apart? The telephone network existed, of course, but it was designed for voice, not data. Voice calls used circuit switching. When you called someone, a physical circuit was established between your phone and theirs, a dedicated path through the network, and that circuit was yours for the duration of the call, whether you were talking or silent. It was wasteful and inflexible. The breakthrough came from an idea called packet switching, developed independently by Paul Baran at the Rand Corporation and Donald Davies at the National Physical Laboratory in Britain. Instead of establishing a dedicated circuit, you'd chop your data into small chunks, packets, each one labeled with the address of its destination. These packets would be sent individually through the network, each one potentially taking a different route, hopping from node to node, and reassembled in the correct order at the destination. If a packet got lost or corrupted along the way, you'd just resend that one packet, not the whole message. The network was resilient, efficient, and could handle many simultaneous conversations by interleaving packets from different sources. In October 1969, a team at Ookla sent the first message over ARPANET, the network funded by ARPA, to a computer at Stanford Research Institute, about 350 miles away. The message was supposed to be login. They got as far as LO before the system crashed. But it was a start. Over the next few years, ARPANET grew, connecting universities and research labs across the country. And the protocols used to manage this network, the rules for how packets were formatted, addressed, and routed, evolved into something called TCP/IP, the Transmission Control Protocol and Internet Protocol, developed primarily by Vint Cerf and Bob Kahn in the 1970s. TCP/IP is the language of the Internet. Every device connected to the Internet, from your phone to a data center in Singapore, speaks TCP/IP. Here's the basic idea. The Internet Protocol handles addressing and routing. Every device gets an IP address, a unique numerical label, and routers throughout the network use these addresses to forward packets toward their destination, like post offices routing letters by zip code. The Transmission Control Protocol handles reliability. It breaks data into packets, numbers them, sends them, waits for acknowledgments from the receiver, and resends anything that gets lost. Together, they create a reliable data channel over an unreliable physical network. It's elegant, and it's the reason you can stream a video from a server 5,000 miles away and have it arrive smoothly on your screen. But the Internet, as a raw technology, was hard to use for most people. You needed to know arcane commands, specific addresses, precise protocols. The thing that made the Internet accessible, that turned it from a tool for researchers into a global phenomenon, was the World Wide Web, invented by Tim Berners-Lee, a British computer scientist working at CERN, the European Particle Physics Laboratory in Geneva, in 1989. Berners-Lee's insight was simple and profound. He combined three ideas: hypertext, which is the concept of documents containing links to other documents. You click a link and it takes you to a different page. A standardized document format called HTML, hypertext markup language that any computer could display, and a protocol called HTTP, Hypertext Transfer Protocol, for requesting and delivering these documents over the Internet. He also wrote the first web browser and the first web server. The whole system was designed to be open, decentralized, and universal. Anyone could create a web page, anyone could link to anyone else's page. No central authority controlled the content or the structure. The web launched to the public in 1991, and the explosion that followed is something you've lived through, or at least grown up in the aftermath of. Mosaic, the first popular graphical web browser, appeared in 1993. Netscape followed in 1994. By the mid-1990s, millions of people were online. By the 2000s, the Internet had transformed commerce, communication, entertainment, education, politics, essentially everything. And all of it runs on the same fundamental stack: transistors and logic gates at the bottom, processors and memory in the middle, operating systems and protocols above that, and applications at the top. The same chain we've been tracing all night. Now, let me circle back to something, because there's an aspect of how computers work that I've been building toward, and it has to do with the limits of the architecture we've been describing. The von Neumann architecture, processor and memory connected by a bus, instructions fetched and executed one at a time, has been the dominant paradigm since the 1940s, and for decades, The way to make computers faster was simply to make the clock speed faster. Run the fetch, decode, execute cycle more times per second. In the 1980s, processors ran at a few megahertz, millions of cycles per second. By the early 2000s, they'd reached several gigahertz, billions of cycles per second. But then something happened. The clock speeds stopped climbing. If you look at the history, processor clock speeds have been roughly flat since around 2004 or 2005, hovering around 3 to 5 gigahertz for most consumer chips. Why? Because of physics. As you push more cycles per second, the transistors switch more frequently, which generates more heat. At the speeds processors were reaching, the chips were getting so hot that they couldn't be cooled effectively. There's a famous story about Intel engineers realizing that if clock speed trends continued, future processors would be as hot as the surface of the sun. Obviously, that wasn't going to happen. They hit a wall. The solution was to stop making individual processors faster, and instead put multiple processors on the same chip. Instead of one CPU core running at 5 gigahertz, you'd have 4 cores, each running at 3 gigahertz, or 8 cores, or 16. Modern high-end chips have dozens of cores. Each core is a complete processor, with its own fetch, decode, execute cycle, capable of running its own stream of instructions independently. Multiple cores can work on different tasks simultaneously, or they can collaborate on a single task if the software is written to take advantage of them. This is parallel computing, and it represents a genuine shift in how software has to be written. A program designed for a single core processor. Do this, then this, then this, all in sequence. Can't automatically take advantage of multiple cores. You have to explicitly divide the work into pieces that can run simultaneously without interfering with each other. That's hard. There are deep theoretical results about how much speedup you can get from parallelism. Amdahl's law says that the speedup is limited by the fraction of the program that can't be parallelized. If 90% of your program can run in parallel, and 10% has to run sequentially, then even with an infinite number of cores, you can never be more than 10 times faster. The sequential part is the bottleneck. But there's another kind of parallelism that turned out to be enormously important, and it came from an unexpected direction: video games. Seriously. The rise of graphics processing units, GPUs, is one of the most consequential developments in modern computing, and it started because gamers wanted better graphics. In the 1990s, as 3D video games became popular, the demand for real-time 3D rendering exploded. Rendering a 3D scene, calculating how light bounces off surfaces, determining which objects are visible from the camera's viewpoint, applying textures and shadows, involves doing the same mathematical operation on millions of data points simultaneously. Each pixel on the screen needs to be calculated, and the calculations for each pixel are mostly independent of each other. This is massively parallel work. CPUs, with their handful of powerful cores optimized for sequential execution, weren't great at this. So companies like NVIDIA and ATI started building specialized chips, GPUs, with thousands of tiny, simple processing cores. Each core was much less powerful than a CPU core, but there were thousands of them, and they could all work on their own little piece of the rendering problem at the same time. A modern GPU might have tens of thousands of cores, each one capable of simple arithmetic, all of them chugging away in parallel on different pixels or vertices or texture calculations. And then, starting in the mid-2000s, people realized that GPUs weren't just good for graphics. They were good for any problem that involved doing the same operation on lots of data simultaneously. Scientific simulations, financial modeling, data analysis, and, crucially, machine learning. This is where the story connects to the technology you interact with every day. the technology that's reshaping the world right now. Machine learning, and particularly the branch of it called deep learning, which uses artificial neural networks, turns out to be almost perfectly suited to GPU computation. Training a neural network involves multiplying enormous matrices of numbers together, millions or billions of times. Matrix multiplication is a textbook example of a massively parallel operation. Each element of the output matrix can be computed independently. GPUs tear through these calculations at speeds that CPUs can't match. The explosion of artificial intelligence that you're living through right now, language models, image recognition, autonomous vehicles, medical diagnosis systems, all of it was enabled, in large part, by the fact that we had these incredibly powerful parallel processors sitting around because people wanted better video games. NVIDIA, a company that spent years making GPUs for gamers, found itself at the center of the AI revolution. Their chips are now the engines driving the training and operation of the world's most advanced AI systems. It's one of those weird, beautiful historical twists that nobody could have predicted. But let me pull all of this together, because I want you to see the full picture of what a modern computer actually is, and what's happening inside it right now, this very second, in the device near your pillow. Start at the bottom. There's a chip, a sliver of silicon, maybe the size of your fingernail. On that chip, there are billions of transistors, tiny switches made from doped silicon, N-type and P-type, arranged into junctions that can be turned on and off by small voltages. Those transistors are wired together into logic gates, AND gates, OR gates, NOT gates, that perform the Boolean operations George Boole described in 1854. Those gates are combined into larger circuits, adders, multiplexers, decoders, that can do arithmetic and route data. Those circuits form the cores of the CPU, each one capable of the fetch-decode-execute cycle that von Neumann described in 1945. The CPU is surrounded by memory, fast cache close in, larger RAM a little further out, permanent storage at the periphery, all organized in a hierarchy designed to keep the processor fed with data at maximum speed. On top of the hardware sits the operating system, a vast, complex piece of software descended from Unix, from the work of Thomson and Ritchie at Bell Labs in the late 1960s. The operating system manages everything, scheduling which programs get to use the CPU, allocating memory, handling input from the touchscreen or keyboard, managing the display, running the networking stack that connects the device to the internet. It's the invisible conductor of the digital orchestra. Above the operating system are the applications, the apps you actually see and use. Each one is written in a high-level programming language, compiled into machine code by the kind of tool Grace Hopper imagined in the early 1950s. Each one uses thousands of libraries and frameworks, building on the work of millions of programmers over decades. And each one, when it needs to do something, display a letter, play a sound, send a message over the network, sends a request down through the layers to the operating system, which translates it into specific instructions for the hardware, which executes those instructions as patterns of transistors switching on and off, which ultimately produces the electrical signals that drive the display, the speaker, the radio antenna, whatever physical effect makes the digital real. The whole thing is connected to the internet through radio waves, Wi-Fi or cellular signals, which are electromagnetic waves, the same phenomenon Maxwell described in the 1860s. Your device encodes data as patterns of radio waves, sends them through the air to a nearby router or cell tower, which sends them through fiber optic cables, pulses of laser light bouncing through hair-thin glass fibers, across cities or continents or oceans, to reach a server in a data center somewhere. That server is itself a computer, running the same basic architecture, transistors, gates, CPU, memory, operating system, and it processes your request and sends data back the same way. The round trip might take a few milliseconds, a few thousandths of a second for your message to cross the planet and come back. Every web page you load, every notification you receive, every message you send is making this journey. And in those data centers, the enormous buildings full of servers that power the cloud, something else is happening. Those servers are connected to each other through incredibly fast networks, pooling their computing power. When you search for something online, your query doesn't go to one computer. It goes to a system that might involve thousands of computers working in concert, each one handling a piece of the problem, scanning different parts of the index, ranking results, personalizing based on your location and history, and the answer comes back to you so fast, it feels like it was already sitting there, waiting for you to ask. It wasn't. It was computed from scratch, in a fraction of a second, by a distributed system of staggering complexity and scale. And here's what I find genuinely awe-inspiring about all of this. The computer in your pocket, a device you might have paid a few $100s for, a device you hold casually in one hand, is more computationally powerful than all the computers that existed in the world combined in 1965. It has more memory than ENIAC had transistors. It can do in a second what would have taken the entire team at Bletchley Park weeks. And it fits in your pocket because of that relentless shrinking of transistors, from the pencil eraser size of Bardeen and Brataine's first device in 1947 to the few nanometer features of today's chips, a reduction in size by a factor of millions. That's what Moore's Law did. That's what the integrated circuit made possible. That's why Kilby and Noyce's invention mattered so much. And the journey isn't over. Right now, chip designers are pushing toward transistors that are just 2 or 3 nanometers across, dimensions where quantum mechanical effects that Bohr and Heisenberg described in the 1920s start to become significant engineering challenges. When a transistor is that small, electrons can quantum tunnel through barriers that are supposed to be solid, causing current to leak where it shouldn't. The insulating layers are just a few atoms thick. At this scale, classical physics breaks down, and chip designers have to account for the probabilistic behavior of individual electrons. The quantum mechanics that once seemed like abstract philosophy is now an everyday engineering constraint in chip fabrication labs. There are ideas for what comes next. New transistor architectures like gate-all-around, where the controlling gate wraps entirely around the channel, giving better control at smaller sizes. New materials beyond silicon, gallium nitride, carbon nanotubes, even two-dimensional materials just 1 atom thick. Some researchers are exploring computing paradigms that move beyond the von Neumann model entirely. Neuromorphic chips that mimic the structure of biological brains, processing information in fundamentally different ways. And of course, quantum computers, which use quantum mechanical phenomena like superposition and entanglement to perform certain types of computations exponentially faster than any classical machine could. But you know what I think is the most remarkable thing about this whole story? It's not the speed of the machines, or the number of transistors, or the scale of the internet, although all of that is staggering. It's the human part. It's the fact that this entire tower of technology, from the abacus to the smartphone, was built by people, one insight at a time. Leibniz dreaming about binary in the 17th century. Boole writing down the algebra of logic in a book that nobody read. Babbage obsessing over gears in his London workshop. Ada Lovelace seeing what a programmable machine could become. Turing imagining the simplest possible computer and proving that it could compute anything. Shannon making the connection between logic and circuits in a master's thesis. Bardeen and Brattain holding 2 gold contacts against a piece of germanium on a December afternoon. Kilby soldering wires to a chip in an empty Texas Instruments lab while everyone else was on vacation. Hopper insisting that computers could understand something close to English, building the proof when nobody believed her. Thompson and Ritchie creating Unix on an abandoned computer in a hallway. Every one of these people was solving the problem right in front of them. Leibniz wasn't thinking about smartphones. Boole wasn't designing the internet. Turing wasn't trying to make TikTok possible. They were each pulling on a thread that interested them, following their curiosity, trying to make one specific thing work. And the threads wove together, over centuries, into something none of them could have imagined. And the machine they collectively built, this thing we casually call a computer, it works the same way tonight as it did the very first time a stored program ran in Manchester in 1948. Transistors switch on and off. Logic gates combine those signals according to the rules of Boolean algebra. Arithmetic circuits add and subtract and multiply binary numbers. A CPU fetches instructions from memory, decodes them, and executes them, one by one, billions of times per second. Software, written in languages that would have astonished the early pioneers, is compiled down through layers of abstraction until it becomes the binary patterns that the hardware understands. Data flows through memory hierarchies, through network cables, through radio waves, across the planet and back, all governed by protocols and standards built on the same fundamental principles. It switches, all the way down. It switches, on and off, 1 and 0, true and false. The simplest possible decision, made billions of times per second, in perfect sequence, with perfect reliability, producing the entire digital world. And right now, as you're lying there, maybe your eyes are getting heavy, maybe the words are starting to blur a little, the device next to you is still doing it. Still switching, still cycling through fetch, decode, execute. The clock signal is still pulsing through the chip, keeping all those billions of transistors in lockstep, like a heartbeat. The operating system is still running, managing processes, checking for notifications, keeping the radios alive in case a message comes in. The display might have dimmed, but the processor is still there, still working, still carrying out the instructions that some programmer wrote, that some compiler translated, that some CPU is faithfully executing, one cycle at a time. It's doing exactly what Turing imagined in 1936, reading a symbol, checking its state, writing a symbol, moving to the next instruction. An infinite loop, but a purposeful one. A machine made of nothing but simple decisions, running the quiet, invisible machinery of the modern world. And the thing that makes it possible, the thing that ties together every part of this story, from the Sumerians' clay tokens to the silicon chips in your phone, is the same insight, rediscovered over and over, across centuries, by people who often didn't know about each other's work. The insight that any complex thing can be built from simple parts, if you have enough of them and you organize them well enough. That counting can become calculating, can become computing, can become thinking, or at least something that looks so much like thinking that the distinction starts to feel like philosophy rather than engineering. That the gap between a pebble on a counting board and a neural network generating language is not a gap of kind, but a gap of scale. It's the same thing, all the way up. Simple operations, composed and layered and stacked, until complexity emerges from simplicity, like a cathedral built from grains of sand. That's how your computer works. That's how all computers work. And as you let go of the day, and your breathing slows, and the thoughts start to soften around the edges, the machines keep running. The transistors keep switching. The electrons keep flowing through their silicon channels, following paths that Bardeen and Brattain and Shockley first carved out in that New Jersey lab nearly 80 years ago. The logic gates keep performing the operations that George Boole described when he sat down to write the laws of thought. The programs keep running, layer upon layer of human ingenuity, compiled and executed and displayed. A cathedral of abstraction so tall you can't see the bottom from the top. It's all just switches, but what extraordinary switches they are. And what an extraordinary thing it is that we figured out how to make them, how to connect them, how to teach them to carry the weight of the modern world on their tiny, tireless shoulders. So let that thought settle. Let the numbers blur. Let the binary fade into the background hum of the universe, where it's always been, where it always will be. The simplest possible answer to the simplest possible question. On or off, yes or no, 1 or 0. And then, quietly, gently, the same way a computer reaches the end of its program and goes to sleep, just like that, you can too.